So we're about to embark upon one of the richest and most interesting areas of linear algebra, and this is where we use the eigenvalues and eigenvectors to create a diagonalization. So what's a diagonalization? Well, a matrix A is diagonalizable if there is an invertible matrix P and a diagonal matrix D such that I can write A as the matrix P times D times P inverse. And it's called a diagonalization because we have a diagonal matrix whose eigenvalues are the same as the eigenvalues of A. And all of that can be proven, but this is what we call a diagonalization. I find these two matrices. I find the P matrix, which is invertible, and I find the D matrix, which is diagonal. Now, not every matrix A is diagonalizable, and so this section is very rich. The difficulty with writing just a single section on this topic is that it's huge in mathematics. It's one of the biggest, richest, deepest subjects, and you'll use eigenvalues all the time in courses like differential equations and PDEs, where they give us some hint about the dynamics of of a of a system. So, and that's not the only place they're used, by the way. But because of that, there's going to be a huge amount of material, and this is just a brief introduction, but it's a very interesting one. And the process isn't that hard. So let me go over that process, then we'll show an example of how to do it, and then we'll come back and look at some interesting facts. So the first thing that Margalit gives us is a definition of diagonalizable, which is the same as what I wrote, except they're using C instead of P for the invertible matrix. And obviously any diagonal matrix D is diagonalizable, but the idea is similar to. So I didn't do a video on matrix similarity, but I did provide links that you should have taken a look at and read. So this is, the idea of similarity isn't huge, but it sort of underpins what's going on with diagonalizability. So the criteria for A being diagonalizable is having linearly independent eigenvectors. If all of the eigenvectors of a matrix are linearly independent, then we can diagonalize it. So that means that a diagonalization requires calculating all of the eigenvalues, because those are going to be the entries on the main diagonal, and then calculating all of the eigenvectors, because as long as we have each eigenvector corresponding to its associated eigenvalue, if we put them in the same order that in C that they are in D, get the associations correct, then that is the recipe for how we're going to do this. We're going to find all the eigenvalues by determining the characteristic polynomial and setting it equal to 0. And then for each eigenvalue, we're going to find a basis for that eigenspace, which is a row reducing the A minus lambda I, augmented with the 0 vector. We're going to be row reducing that matrix, writing the results in vector form. Well, that basis that we create for that eigenspace is composed of the eigenvectors. So then after we've done that for every possible eigenspace, then we can create this diagonalization if it's possible. It's not always possible. Now there are some times we know it's possible. As long as we have n distinct eigenvalues, then I know the matrix is diagonalizable. That's really helpful. But sometimes when I'm factoring a polynomial, I get multiplicities, right, that are higher than 1, right? So something like x cubed, when I set it equal to 0, I get 1 root, right? I get 0 as the only root, and that root has multiplicity 3. So eigenvalues also come with multiplicities. If all those multiplicities are 1, if I get all n of them to be completely distinct from all the others, then I definitely have a diagonalizable matrix. When when I have a multiplicity higher than 1, when I factor that polynomial, that's when there's a question about whether or not it can be diagonalized. Some can, some can't. And I went over this before, but the recipe, the task of diagonalization, you find the characteristic polynomial. How? By taking the determinant of a minus lambda I. When you solve that out algebraically and set it equal to 0 and factor, you find all the eigenvalues. Then for each eigenvalue, you calculate a basis for the eigenspace, which is the null space of the matrix A minus lambda I for that particular lambda. And again, this is where you find out whether or not. So this is a lot of algebra and linear algebra to find out that it's not diagonalizable, but this is where you find out. As long as you end up with n linearly independent eigenvectors, then you create it how? Well, the matrix C is just a list of all the eigenvectors, and you make sure that they're in the same order as you list the eigenvalues in the diagonal matrix. So let's try a couple examples of this. Okay, so here we are with a 3 by 3, and this is going to be a little bit challenging, as you'll see when I do the characteristics polynomial. But first I need simx. Again, this is in the symbolic mathematics toolbox, which you can download. It's a package that goes with MATLAB. And when I do that, I can say y equals char poly of a, and then I specify the x, which is optional, but it tells it what variable that I want to create this polynomial in. And the challenging part is going to be the 60. Now it's not impossible, right? But 60 has a 2 and a 5, a couple of 2's and a 5 and a 3 in its prime factorization. So we've got lots of different factors to try to break this down. So we have to find one. So we're going to search for it using, right, we are going to use the polynomial long division basically, and we're going to have the remainder in the quotient. And the polynomial long division is this polynomial reduce function. So I'm going to put in y, and then I get to start putting in the different factors that I want to try. So I'm going to start with the 5's. Something had to create that 60, and I nailed it first time. By the way, I just got lucky. But that's, again, something had to have that factor of 10, factor of 5 in there somehow to get to 60. So it seemed like a good place to start. Like with the, why didn't I start with 2's and 4's? Well, there's just lots more. There's double the chances. I would guess that something with a 3 in it might also work, but who knows? We'll know in just a second. So then what I can do is I can polynomial reduce the q. So here I want to, oh wait, I don't need to polynomial reduce the q. I can actually see this, right? 12, I have -4 and -3, right? So my lambdas are equal to the, let's see, -3, -4, and +5, right? Wait, I'm sorry. 3, 4, and 5. Right, so what I'm saying is that I'm seeing that I should be able to factor q into x minus 3 times x minus 4. Right, so that should work. And when I multiply the -3 and the -4, I get the +12. When I add the -3x and the -4x, I get -7x. But those are the factors, so the actual roots are 3, 4, and of course, if x minus 5 was a factor, then +5 is also a factor. All right, well, that's cool. And then again, there's always a quick way to check. If we're going to use a computer to do algebra, we might as well use it to check, right? So I'm going to expand. Well, here, let me create the thing that I want to create. Let's use like w equals, and then let's create x minus 3 times x minus 4 times x minus 5. And if that's our w, then you'll see that we can expand it. So I just do expand W. And since these are my guesses for what the factorization was, right? So I'm guessing here that this is the correct factorization of this. So when I expand it, it should come out the same. And you'll notice I do have the x cubed minus 12x, right? Check. X cubed minus 12x plus 47, or minus 12x squared plus 47x minus 60. Yep. So we get a match. Okay, so what do we know? We know that we have the correct eigenvalues. So nothing else is really all that important. So I'm going to delete it and just save some space here. Okay, so these are our eigenvalues. Now what? Well, we have to calculate an eigenspace for each of them. All right, so let's talk about what we're doing. So I'm going to take A minus lambda I. Well, the first lambda is 3, so times the identity matrix. My n is 3. It's a 3 by 3 matrix A. So my identity matrix is going to be size 3 by 3. And that's what I want to calculate, which you can see, right? That it's just taking 4 minus 3 and getting me 1. And then it's taking 13 minus 3 for the 10, and then minus 5 minus 3 to give me minus 8. Well, okay, yay. But I want to augment that with a 0 vector, right? I want zeros here in an augmented matrix. And I can accomplish that all in one step along with the row reduction. I just wanted to show you what I was doing. So I'm going to wrap this, right? I'm going to do and RREF on the outside, and then I'm going to do a square brackets. Why? Well, the square brackets is where I'm going to augment. So when I use the square brackets and the comma, then I can do zeros, 3 comma 1. That'll create a 0 vector that I need. And then I close the parentheses. So all in one step, let's see if I can break that down, right? So this is the A minus lambda I. The square brackets, comma, zeros is going to augment the 0 vector that I need. And so now I have the augmented matrix that I want in the square brackets, so I just RREF it. Okay, so let's see that. Okay, so this is kind of cool. It's not too bad. Let's switch to some text. So I get x sub 1 has to equal negative x sub 3. X sub 3 is my free variable. Then I get x sub 2 equals x sub 3, right? With x sub 3 is free. And we don't really need that much help, but let's do, I'm going to call this V3. Why? I'm thinking of it as a V with a subscript 3 to correspond to the eigenvalue of 3. And what does it need to be? Well, x sub 1 needs to be the opposite sign, x sub 2 is equal, and then x sub 3 is free. So this is what I believe is the correct eigenvalue. And I'm trying to save some space so everything can be seen. Let me get rid of this stuff. Again, I don't expect you to write all of that out. If you can go, you should, when the eigenvectors are easy, like they are here. We should be able to write down, we should be able to kind of solve this in our head and write down what has to be. Just remember that the free variable is always going to be 1, and then try to figure out what the other two have to be. And also if I have fractions, I'm allowed to set the free variable high enough that it clears out the denominator. So if I had fourths in my denominators, I could set my free variable at 4, and then I get to cancel out the fractions, which I've shown in the previous video. All right, so how do I check? Well, I take A times V3 and see what I get. And you'll notice that it works. That I had a minus plus plus, and they're all 1s, and now I have all 3s with the minus plus plus pattern. So yes, and I've shown this before, but it's also possible to do the 3 times V3, equal. The double equal is the conditional that checks, and when I get a logical array with all 1s, that means that that statement here is true. All right, so now I have one of the eigenvectors, and I am going to copy paste it up here. Boom. So V3. And then what I'm going to do is I'm going to work on the 4. So that's not too bad. Everything stays the same except now when I do a minus lambda I, the lambda is a 4. And so now I row reduce. Now this is interesting. Okay, so this is interesting. Okay, so this v4 is the 0 vector. Okay, so let's talk about that. This is a great example. And then let's check it out, right? So that's the 0 vector, and then a times v4, and let's see what it comes out to. Um, okay. Oh, wait. I'm sorry. The x sub 1 has to be equal to 0. Let me look at this, right? So x sub 1 equals 0. Man, I'm doing this badly. X sub 1 equals 0. X sub 2 equals 0, and x sub 3 is free. Okay, so then what we need here is we need a 1. There we go. Okay, so what I got confused by, remember, 0 can be an eigenvalue, but the 0 vector cannot be an eigenvector. Okay, and I was thinking we had hit on one, but you know, that would showcase what could be 0 and what couldn't, but I just screwed up is what happened. But here we go. So now if we have this matrix 0, 0, 1, and this isn't working. I'm gonna have to think about this one. I'm gonna pause the video here and think about this. Oh yeah, I'm an idiot. Okay, that's what I thought about. Um, this is x2, this is x3, so my free variable is sitting over here in x1. All right, so let's go here and let's just switch. Switch this to a 1, switch this to a 0. There we go. Okay. Wow. All right. So my vector had a 1 with 2 zeros, and the eigenvalue is 4, and then here we go, 4, 0, 0. So now we have it. Sorry, I botched that. I was getting excited about something that simply wasn't true. So let me jump up here, throw that one in. We know V4 and V3. Sorry, V4 and V3, and boom. Okay. So the last thing we need to do here is do it for 5, right? So I just, now that I have this set up where it creates the augmented matrix and row reduces, I just switch out my lambdas, bang, there we go. Now this is interesting. Let me think about this one. So I hopefully get it right. So V5, thinking of V sub 5 connected to the lambda value, the lambda equals 5 eigenvalue. And so I'm going to put a 4 in for x sub 3. Why? Well, because I have a 1/4 and a 5/4, right? And so that's what's going to get moved over. But when they get moved over, this is the one that'll be negative, right? So I think this will work, right? -1 and 5. And then let's check it out. And you see that this did in fact work, right? I think it did here. So -5 times 5 is -1 times 5 is -5. 5 times 5 is 25, and 4 times 5 is 20. Okay, so again, that's what I did. You know, I was thinking of, hey, what if I put a 4 here? Yeah, if I put a 4 here to clear out this denominator, because why? Because I had the 1/4, right, and the 5/4 that got subtracted over this way. With this one negative. So, well, if I make it a 4, then I'm just grabbing the numerators, and that's where I got the 5, and the -1 was from the numerators after these guys moved over to the right side of the equal sign. Okay, so now we have it. Okay, let me copy paste V5 up here so we've got the whole thing, the whole shooting match. All right, and now we should be able to create these matrices, right? So I think D, I'm pretty sure that diag will take this, this is why I wrote them this way. Oh, I called them lamma. Hang on, that's bad. Lambda, okay. Duh. I think when I do diag lambda, right, that's why I wrote them as this vector. Because this row vector, because then when I use the diag function, it creates a diagonal matrix, and so that's the correct D that I need. And then let's use C, that's what the book uses. So C, what that is just a list of the eigenvectors, but they have to be in the same order, right? And that's one reason why I kind of put them in the same order, you know, with the subscripts matching the eigenvalues, so I can kind of make sure that I line them up properly. So what I'm supposed to be doing here is V3, comma, V4, comma, V5, right? And that'll be my C matrix. Okay, and now what I should be able to do, if everything's working properly, is multiply these guys out and see it all work. So remember, what I'm trying to get is I'm trying to match up A. That's what I want. I want something that matches A. Okay? And when I try it, let's do the multiplication. C times D times the inverse, times the inverse of C. Boom. And it's kind of hard to see, so let's just put A again. And there you go. You can see that they are in fact identical, which is cool. Now, one thing that the book mentions that's important is this is not unique, right? I can switch this around, right? I could have done in my diagonal matrix D, I could have done 5, 4, 3 or 5, 3, 4, and then that would have changed the order of the columns of C. So there's lots of different ways I could have done it. Also, eigenvectors themselves aren't unique. So as long as I'm using an eigenvalue, an eigenvector that corresponds to the eigenvalue, it works, which is kind of crazy that that there's so many different ones that work and that they all come out to be the same thing. They all come out to be A. Okay, so normally 4x4s are pretty hard to do, and it comes down to factoring this characteristic polynomial, but if you've got a computer, you can do it pretty easily. So let's just calculate this characteristic polynomial. And actually, this is the kind you'll find in books a lot, where you don't have to factor a 4th or 5th degree or maybe even 6th degree polynomial. They'll give you you know, an x to factor out. So that's the first thing we should factor. So let's do the, let's say, so y equals the char poly x, all right, and now we're going to do the polynomial reduce y by x, and oh, I forgot the rq, sorry. So we're going to get two outputs from the function, the remainder and the quotient this way. So remainder is 0, and now I need to factor this. And this is interesting. Maybe I picked a bad example. I didn't factor this one all the way, but let's do it. Let's say that RQ2 equals the polynomial reduce Q comma, and then, right, x minus 1. And that worked. Oh, cool. And then right, that reduces as well. I'm just going to do it this way to get them all right. So I can do RQ3, do this one, Q2, and it looks like to me that x minus 1 is in there again, right? So we have some interesting stuff. We have a eigenvalue of 0, and we have an eigenvalue of 1 that repeats itself 3 times. Okay, so what we're saying is that in factored form, y equals x times x minus 1 quantity cubed. Okay, so again, we can try to expand that and see if it works. So I'm going to do W again. W equals x minus 1 quantity cubed times x, boom, um, times x, boom, and then I'm going to expand x, um, expand x, expand w, okay? Um, and yes, they match. Another way to check is if expand w equals y. And no, well, that put them both on the same line. It doesn't do a, it doesn't check it, um, but you puts them on the same line and you can see that they're definitely the same thing. All right, so we have the correct factored form, but now the interesting thing is that we know that our lambdas, there's just two of them, and 0 and 1 are the only ones we got. Okay, so let's get rid of all this. And so what are we going to do now? Well, we're going to row reduce, right? So what are we going to row reduce? We're going to row reduce A minus lambda I. And so A minus 0 times lambda I is just I. So excuse me, it's just the 0 matrix. So at first, we're just row reducing A augmented with the 0 matrix. This time it needs to be 4 by 1, right? I need a 0 vector that matches the number of rows in A. So since it's a 4 by 4, I need the zeros 4 by 1. I'm going to row reduce that, and it needs to be in square brackets so that it augments the A in the 0 matrix. And then there we go. So then now notice this is interesting, right? So even though I was using the 0 eigenvalue, the eigenvector is not going to come out to be 0. And let's see if I can do this all in my head. Probably can't. Um, so I'm going to the final one, right? Because I know that x sub 4 is free. And I'm going to have thirds in the denominator, so I'm going to use a 3. Okay. Well, so when I solve for this one, I'm going to have a positive 1/3 over here. So I know that this number needs to be, let's see, so I know that, let me just write it out. So I know that x sub 1 equals 1/3 of the x sub 3. All right, well, that's cool. So then I know that I want a 1 here. And in second position, I have the exact same equation, so I'll want a 1 here as well. And then in the next equation, it's actually going to be negative, and it's going to be 2/3 instead of 1/3. So this is going to be 1, 1, negative 2, 3. So it helped to write the first one out, and hopefully you can see that. So I'm leaving it just V for the V0 vector. And let me put a semicolon after that for just a moment, and then let's try it. So A times V. Now, so this is what's interesting, is that obviously if 0 is an eigenvalue, right, then what we're expecting this to work is 0 times the vector V, which is going to crush it, right? It is going to be the 0 vector. But notice that I took a non-zero matrix A, right, this matrix, and I multiplied it by a non-zero vector V. But the result of that multiplication comes out to be the 0 vector, right? The result is the 0 vector because the eigenvalue is 0. So this is the interesting example I was looking for before, and this is where I made my mistake. I can get a result vector that's all 0, and that's what you get because of this 0 eigenvalue part of this equation. All right, so we have V0, right? So let's semicolon that and go looking for V1. And there should be lots of, right, there should be lots of free variables, right? Because Here's what I'm looking at, right? So I've got multiplicity 3 for this eigenvalue of 1, and I can have up to 3, right? Up to 3 linearly independent eigenvectors. So this matrix will be diagonalizable if all three, if it generates 3 free variables and therefore 3 linearly independent eigenvalues or eigenvectors, right? If the basis for this null space has 3 component vectors, but if the basis only has 1 or 2, then the matrix is not diagonalizable. So I haven't done this example yet. I don't know how it's going to turn out. But we can certainly find out by doing what? Well, I row reduce A minus lambda times the identity matrix of size 4. And drum roll, we get to see what we get when I get rid of that V1. Oh, and I take the semicolon off so we can see. So yeah, now this is interesting. Looks like we're only going to get 2 linearly independent eigenvalues. So what we do to get the different eigenvalues right is that we set the free variables, and the three free variables are right here, right? And so the way I get different eigenvectors is I set all of the well, this might work. Let's see how it goes. So we set all of the free variables equal to 0 except for 1. So what I'm going to do is I'm going to start off by setting these 2 free variables equal to 0 and solving. And so let me call that v sub 1, 1 vector. And what happens? Well, I'll get a 0, right? I'm setting the second one equal to 0. The fourth one is already equal to 0. Sorry, this is going to be a minus 2 over here. Sorry. So when I subtract, I'll get the minus 2. Let me show that one, right? So what I'm doing is I'm setting this one equal to 0. Then I have x sub 1 equals minus 2 times x sub 3. And remember the this one was already 0. We're setting it equal to 0, but it's already 0. So then when x sub 3 is equal to 1, then I know that my first variable is equal to minus 2. All right, so that should be an eigenvector, and of course we can check. So let's do a times v11, boom. And of course our eigenvalue is 1, so what this multiplication should do, right, is just return the same vector, and it does. Okay, so we've got one that works. Okay, so let's take v sub 1, 1 and put it up here with v, so we're getting closer. And then let's create our matrix v1, 2, well, let's write it down. I can't. So I want a minus 4, and then a 1, and then a 0, and then a 0, right? So we're setting everything equal to 0. Setting everything equal to 0, then the 4 comes over here. It's negative. When it does come over, right, and remember we're setting these guys equal to 0. There you go. So I kind of did this in a weird order, I guess. I guess here we set the second and the fourth one equal to 0. Here we're setting the third and the fourth one equal to 0, but it still should work, even though it might have been the most straightforward order. So when I do this, right, notice that I get the same thing as above, right? I take a vector, negative 4, 1, 0, 0, and when I multiply it by a, I get the same thing out, which makes sense because I'm taking 1 times this vector v sub 1, 2, right? Because my eigenvalue is 1, so the same vector pops out, and that's cool. So I've got another one v sub 1, 2. Oh wait, I can just copy paste if I'm not a dummy. There we go. Okay, and then the question is, what happens when we set these two guys equal to 0, these two free variables equal to 0? Well, then I just get, I get 1 equals 0, which is a problem, right? Because the v sub 1, 3, right? So v1, 3 is just a 0 vector, right? And yeah, it works, but of course it works. The 0 vector will always work. So then here's our problem. This is linearly dependent no matter what set of vectors I put it in, right? Any set of vectors with a 0 vector in it is linearly dependent. Therefore, the set of all eigenvectors of the matrix are not linearly independent, and therefore it's not diagonalizable. Okay, so that was a long example. Even imagine how much longer it would have been if we did all of this characteristic polynomial long division by hand. So you should be able to do that. You know, factoring a polynomial is a skill, is a prerequisite skill in classes you've taken prior to this. But in this course, you're generally going to be allowed, well, let me put it this way. On the final exam, you're going to be allowed to do the characteristic polynomial factorization in MATLAB. However, if you don't have the symbolic mathematics toolbox, you are going to have to do it by hand. And it's not that bad, but since we have to do a lot of factoring of these polynomials, and since you have a computer, I won't always just give you 3x3s. So this is definitely a good example to take a look at. So just to finish up, just want to be clear that diagonalizability has nothing to do with invertibility, and they actually give examples of matrices. The first one is both diagonalizable and invertible. The last one is neither. This one can be inverted, can be diagonalized but not inverted. This one can be inverted but not diagonalized. The geometry of diagonalizable matrices is very interesting. So it just scales the coordinate axis. Now there is a new coordinate system, right? The eigenvectors are creating a new coordinate system, but that diagonal matrix is just doing the scaling along those different axes. So it really is interesting geometry. And then the final note that we'll make is that when we are talking about diagonalizable matrices, they're similar if and only if they have an identical characteristic polynomial. Now that's pretty cool, because if they have the identical characteristic polynomial, they also have the same eigenvalues with the same algebraic multiplicities. So all matrices that are similar have the same characteristic polynomial, and that's a big deal. So definitely learn how to diagonalize these matrices, and that will be on the final exam.